couple of students ask about, hang on, make sure my audio is working. Ask about the homework problem where you're asked to write a standard matrix that rotates a vector in R2 through a particular number of radians. So here I put theta radians. There is a formula that you can use in the homework, but for those, and I totally respect this opinion, that don't want to really use these formulas without understanding where they come from, this video is going to go through where exactly that formula is coming from. So the first thing is to recall there's a theorem in section 1.9, I believe, that says that you can generate the first column of the standard matrix for a particular transformation by applying the transformation to the first unit vector. And then you can generate the second column by applying the transformation to the second unit vector. And then you could keep going. If we're working in, say, R4, you could generate the third column with T of the third unit vector and so on. Real quick background on why this works. I'll take the particular case of R2. So when you, let's say this is a transformation from R2 to R2. So the first unit vector looks like this. Just, you have 0 in every entry except the first entry for the first unit vector. And so if we're trying to find the standard matrix A, then this should be equal to A times this vector. Ooh, this is supposed to be a 1. 1, 0. Now, if you think about the way this matrix vector product is computed, then remember what you do is you take the first entry here, 1, times the first column. Let me just put first column of A. Right? And then you do the next entry, so in this case 0, times the second column. I'm just going to call this A2 for the second column of A. And then if it was a larger matrix, you'd have 0 times the third column, 0 times the fourth column, and so on. But so you end up with, this is just by virtue of the way that a matrix vector product is computed, you have 1 times the first column, 0 times every other column. So that's why this, T of E1, generates the first column of A. Okay, and then we could do the same thing. I mean, you probably get the picture, but if we do T of E2, if that's equal to this standard matrix times 0, 1, then the way that's computed is we would do 0 times the first column. I'm just going to put A1 for the first column of A. Because it'd be this entry times first column, and then this entry times second column. So 1 times the second column. Sorry about the handwriting. But so we have 0 times the first column, 1 times the second column, so that's why this generates the second column of A. Okay, so all of that is just to give you the reasoning behind that theorem there. I'm going to pause while I erase. All right, so now I want to get into the particulars of this problem that you have in the homework. So we could generate the first column of this matrix A. First column of A by applying the transformation to the first unit vector, 1, 0. Okay, and I want to draw a picture of this. So if we draw a picture, use blue for the vector 1, 0 here, E1, would be a vector. We could represent it as an arrow starting at the origin and ending at the point 1, 0. So that's going to be this point 1 unit out on the x-axis. Now T of E1. So if we rotate the vector through theta radians, so whatever theta is, then T of, oops, let me try that again. T of E1, all right, something like that. And that's where this right here is theta radians. Now think about the unit circle, or you have to think back to trigonometry. We're going to be using trigonometry here. So if we rotate this theta radians, this vector is 1 unit long. So all we did is rotate it. We didn't change the length. So this vector is still 1 unit long. This point right here is 1 unit out from the origin. And so if you think about the definitions of your trig functions, one way that, let's go with the cosine function, is defined is x over r, those x, y, r coordinates. And that's where x, y is a point on, we call it the terminal side of the angle theta. So this point right here is x, y. R is the distance out from the origin, which in this case is 1. So cosine of theta is equal to just x over 1, so just x. Okay, so that means that the x-coordinate for our transformed vector over here is x is equal to cosine of theta. So t of E1, the x-coordinate, is cosine theta. And the y-coordinate, actually, if you remember, let me write it this way, sine of theta is equal to y over r. Again, we started with the unit vector. This is 1 unit out. It's a unit vector that's just been rotated. So r, the distance from the origin, is 1. We don't know what y is, but so y actually is equal to sine of theta. Because in these problems, you are given the angle theta. So you can compute you can generate, let's say it that way, you can generate the first column of A using these coordinates. So I'm going to build my matrix A up here. So first column is going to be cosine theta, sine theta, based on what we saw happen here. You rotate theta radians, you end up with this point, cosine theta, comma, sine theta. So that's your t of E1. Okay, so we can get the second column by finding t of E2. And that one gets a little bit more complicated. But so t of E2, let's see if I can write it down here. That's t of 0, 1. So let me erase a little bit of what's over here. We're going to do something similar, but we have to instead start at the point 0, 1. So 1 unit out on the y-axis. Okay, so I'll draw that. I guess I'll use green. Draw that here. I think I may have said E1 earlier when I meant E2. So this is the vector E2, which is 0, 1. And then we want to rotate that through theta radians. So try to draw a similar angle theta. So we're going to end up somewhere like about here. So this right here is theta radians. Now I want to use trigonometry again. But this business about cosine theta equals x over r, sine theta equals y over r, when you covered that in trigonometry, that's always starting at what we call the polar axis is one name for it. But we always start at the positive x-axis and rotate from here in trigonometry when we're talking about an angle or rotation theta in a standard position. Maybe that rings a bell. So let me get this E2's in the way. But in this case, we're starting on the positive y-axis. So that changes things a bit. So what we have to acknowledge is, all right, but if we're measuring theta starting at the positive y-axis, then if we back it up, we've got an additional pi over 2 radians. Sorry about this. Pi over 2 radians right here. I really need to get a different writing tablet. Okay, right there. So overall, this rotation is this color. Overall, that is very sloppy, but it is theta plus pi over 2 radians. So, for the terminal side here, we could say now that the x-coordinate is cosine of theta plus pi over 2 radians. And the y-coordinate is sine of theta plus pi over 2 radians. And now you have to use some formulas from trig. And I want this video to end soon, so I'm going to go through this trig part fairly quickly. Okay, so angle addition formula for cosine. If you look this up, cosine of A plus B is equal to cosine of A, which in this case is theta, times cosine of B. So times cosine of pi over 2. I'm going to jot the formula down on top of this real quick. If you look up angle addition formula for cosine, you're going to see this. Cosine A, cosine B. Oh my goodness. Minus sine A, sine B. For sine, while I'm talking about it, sine of A plus B is equal to sine of A times cosine of B plus sine of B cosine of A. Okay, so those are just straight formulas from trigonometry. So in this case, A is theta, B is pi over 2. So applying this formula for cosine, it's going to be cosine of theta times cosine of pi over 2 minus sine of theta times sine of pi over 2. Now cosine of pi over 2 is 0 and sine of pi over 2 is 1. So this is cosine theta times 0, so that whole thing's 0, minus sine of theta times 1. So this is all equal to negative sine theta. And that's going to be the x-coordinate for t of E2. So this right here is negative sine of theta. Now applying the angle addition formula for sine, so sine of A, that's sine of theta, times cosine of B, that's cosine of pi over 2, plus sine of B, so that's sine of pi over 2, times cosine of A, that's cosine of theta. Okay, cosine of pi over 2 right here, that's 0. Sine of pi over 2 right here, that's 1. So this is sine of theta times 0, so that whole first part is 0, plus sine of pi over 2, which is 1, times cosine of theta. So this all comes out, when you simplify, you get just cosine theta. So this second entry here is cosine of theta. And then that right there is the formula that you're given in the homework. So when you want to generate a matrix that rotates vectors in R2 through any particular angle, because rotation is a common, I mean, if you just picture image processing, if you want to rotate an image any particular number of degrees or radians, you can apply this formula here. We don't want to do this specifically for one specific rotation. We want to write a matrix that can rotate however much we want. So if you wrote like an algorithm in a computer program to rotate your image, now you could let your user input, I want to rotate this many degrees. They could just input the amount of rotation, and then you could have your algorithm generate the, each individual pixel. The transform pixel ends up here based on this formula.